Hello everyone, welcome to the channel and welcome to Proximal Policy Optimization Coded, where this time we're going to be going through and actually coding Proximal Policy Optimization, not quite from scratch. I have a base that we will essentially work with that does a little bit of the monotonous work, some of the stuff that's not specific to Proximal Policy Optimization, so we can go ahead and get started right on the sort of meat of it, the training and all that sort of thing. So just a heads up, if you don't know what proximal policy optimization is, it is essentially a reinforcement learning training method that works really well, is fairly data efficient for an kind of on-policy method. I have another video talking about the sort of theory behind this, so if you're not sure what's going on and you're curious as to how this works, definitely feel free to check that out first, and it will hopefully explain that away and help you understand what's going on. But if you do just want to know how to code this, well, this is the video for you. So let's go ahead and get to this. I'll start out right now by explaining sort of what I have here and what we're starting with. So this is a very standard, this is in a Google Colab. I'll link this in the description, by the way, if you want to follow along. But this is essentially a base reinforcement learning setup. So I have a few imports right here. We are using PyTorch. I set the device to the CPU. We can change this to the GPU later if we want to. And then I say we're using I essentially have this actor critic network. All this does is it takes in an observation and then it outputs a value and a policy. So pretty standard stuff right here for reinforcement learning. Now I've made notes where we will need to add stuff in for later. But then here I have a rollout function. So this just takes in the model and the environment and it will do a rollout. It doesn't actually do any training. It just samples an action from the policy, uses that action as the use that sampled action as the action for the step, records the reward, and then just returns that reward at the end of it. It also returns training data, but is not being populated right now because we don't know what we'll need to use yet, so we'll go through that. We then instantiate the environment and the model. Let me zoom in a little bit, by the way, I almost forgot. Hopefully this is good enough to see. And then we go ahead and just testing the rollout function right here. So if we go ahead and run that, it will instantiate. Good, looks like it's successful. And then we have a training loop. Now the training loop isn't actually doing anything yet. We're just essentially we're calling the rollout for each episode, appending the reward that we get so we can keep track of it, and printing out the reward so we can keep track of it, but no training yet. That's what we're doing in this video. Cool, so you can see this works, no training, so the reward isn't going up. And the environment we'll be using is cart pull. Now this is a very standard environment. Essentially, you just have this little cart here on the right, and your goal, you get I think the position of the cart and the angle of the pull as the input for the observation. And then you have two possible actions, moving left or moving right. If you move left, the cart moves left, exactly what you'd expect. And the goal is to keep the pull upright as long as you can. And you get one reward for each episode it's staying up. And we're capping the maximum episodes at the maximum turn amount at 200. So we're aiming for a 200 average reward. That will be our goal at the end of this. Now, if this is the stuff you like, you're into this sort of thing, feel free to subscribe to the channel. I do a lot of stuff like this, and I really appreciate all and any of the support I get. So anyway, really jumping into it now, I want to start by recording or saving some data in our rollout. Because right now we're not saving any data when we do the rollout. Well, we need to make sure we're recording the right data so we can use it for training later. So let's go ahead over here to the rollout and think about what we need. So I've actually saved the proximal policy optimization formula here. So this is our maximization function, this L clip, and this L CPI, this is just a subpart of this L clip. So we'll need the old action probabilities. So these are the action probabilities when we are actually doing the simulation. We will be calculating these new probabilities. So for that, we'll need the states and the actions that we took. We will need the advantages, so we can calculate those. We can calculate estimates for the advantages. And I think I want to say that's all. Yeah, I think that's it. We might also need the reward for something. Yeah, we use the reward right here too. So we'll also need the reward. So yeah, let's get to that. That's the list of things you want to save. So we can do that right here. Record the training data after we take a step in the environment. So what I'm going to do is I'm going to say for I, or actually I'm going to change this a little bit. So for I, I'm going to have a different list for each type of data we're saving. So we're going to have the observations, the actions, the rewards, the values, and then the action probabilities. So just so we don't forget, observations, actions, reward, values, acts, log, probs. Cool. So we'll be storing them in here. So we're going to say for item and enumerate. Now we're going to enumerate through each of these items. And this is just a fancy way of doing this. You could do this in several lines, but this is a little bit more compact. So act log probs. We are going to train data I. So I is essentially the current one of these we're on. We're going to just append item. So this should essentially work so that every step we append the latest observation to this array, or list, the latest action to this list, and so on. So we end up with all the data. And then we're already returning trained data here, so that should be good. We can go ahead and do a quick test. So if we do this, we're running, if item is not defined, item in, where is it? Item, that's the problem. Do a quick test, looks good. So let's see this. So if we do train data 0, first we have the observations, right? So if we do train data 0 dot shape, I forget if it's, it's a list. So if we do, we should have numpy imported dot array. This should be the shape of our observations. Yep, it's 16 because that means we had 16 steps. And then we have 4 input observations. We can double check that with the environment by doing m.observation space. And we can see we get 1, 2, 3. Oh, that's weird. Hold on. Oh no, this, let me go ahead and check this for you guys real quick. I'll be right back in a second. Oh wait, no. I'm an idiot. So this is the minimum values we can get. This is the maximum values we can get, but we can have 4 values. So 4 is how many values we'll get per step. We have 4, so that looks good. We're not going to check any of the other ones just for the sake of time, but we're storing all our training data. This is great. Now that we have this, we can go ahead and do the next thing, which will be actually basically passing this off to, I guess we can go ahead and start on the Proximal Policy Optimization Trainer. So let's come up here. And sorry if there's background noise, by the way. There's a bunch of kids playing outside right now, it seems. So we're going to create the trainer here. We're going to make a new class for it called PPO Trainer. And so let's define an initialization function. And we're going to be passing in self, actor, critic. And this is just our model, our policy and value model. Then we're going to have PPO clip value. This is going to be the clip value for the PPO function. By default, we're going to set this to 0.2. That was what worked really well in the paper. Target KL. Divergence, we're going to target 0.01. This is another common value. This is essentially how far we want to get from the policy before we stop doing updates, because remember, we do multiple updates in proximal policy optimization, and the KL divergence, checking that and making sure it doesn't go too far, is how we make sure we don't go overboard and ruin our learning process. So then that's policy train iters, set this to 80. So this is how many times we'll update the policy, assuming we don't go over the KL divergence limit. Otherwise, this will be stopped off early. And then we are going to do the same thing for value train iters, except for there's no max here because this will always be doing 80 times. And then last two things is the policy learning rate, policy LR. And this we'll just set this to 3e-4. Now you can mess around with this if you want, but I already tested this, so I know this works. And value learning rate will be 1e-2. Again, you can play around with these values. I've just played around with them already. That's why I know these happen to work. I would generally start lower is better though if you're not sure what you could actually either, you could use whatever way you want. So we're going to go ahead and set a few variables. I'm just going to copy them over. Nothing too special. We're just setting these to these class variables so we don't lose them. The next thing we want to do is we want to make optimizers. I'm going to do that in here. So we want different optimizers for the policy and value functions because we might want different learning rates for them, like right here, right? So in PyTorch, to do that, what we need to do is grab the parameters for the policy. This is fairly simple. So we just get a list of these. Remember, ACs are actor critic. So there's shared layers. These are layers that are shared between the policy and the value networks. So we grab those parameters and then we concatenate those with the policy specific layers, and these are all of our policy weights or parameters. And then in one more line, we can go ahead and essentially create an atom optimizer. You don't have to use an atom optimizer. It's just when I don't know what to use, I tend to go with atom. It works pretty well most of the time. So we pass in those parameters and our policy learning rate. And then the last thing right here is we'll do the exact same thing, but for value. So we get the value parameters and make an optimizer for the value function. So this is just kind of sort of pre-setup, nothing too interesting. Now we get into the interesting stuff, right? So the train policy. Now, how are we going to train this? What do we need? Well, we need, first self right there. We're going to need the observations, right? This is everything we listed before. We need the observations. We need the actions. We need the log probabilities for the previous function, right? So everything we're passing here. Now, we don't actually need the rewards and the values. The reason we recorded them here is because we are going to use these to essentially estimate the advantages. Or I forget if we use rewards to estimate advantages. I think we do, if I'm not mistaken. So to do that, we'll handle that in a bit, but for right now, we can just assume we're going to get those. And we are going to be estimating the advantages with a method called general advantage estimates or estimation. So GAE for short. You'll see what that is when we get there, but these will essentially be the advantages. So this is everything we need. So what do we want to do? Well, the first thing we want to do is say self.policyOptimizer.0grad, just zeroing out the gradient. And then we start doing the actual interesting stuff. So if I go back over here to our functions, the first thing we want to do is calculate this up here, this LCPI, where we have essentially it's a policy ratio, right? So first let's go ahead and calculate this policy ratio. To do that, we'll need to calculate these new policy logits, or logits, I think it's logits, I don't know. And then we'll need to put those over our old policy logits, and that will give us a ratio. So let's go ahead and do that. So let's calculate the new logits. This will be the self.ac.policy. So this is our policy function. We're going to pass in our observations, right? So these will get us our new logits. And from here, let's go ahead and say new logits equals categorical. So this is a distribution. And we're going to pass in logits equals new logits. And then we can get the actual new log probs. Now, this is totally just a design choice. I'm opting to get the log probabilities. If we look at the function here, you might say, well, why are you doing that? These aren't the log probabilities here. And we'll convert it back. It just tends to be, I think, a little bit cleaner when we do it this way. No particular reason, but we will end up with the same formula. So just follow along until we get to that point, and then I think it will hopefully make sense. So it'll equal the new logits dot log prob acts. So these are the actions we're taking. We're taking the new policy and trying to figure out what the action probabilities would be for the same actions we took before. Now acts, this should be acts, not act. So now we also have the old log probabilities. So what we can do now is just put these one over the other, right? And this is sort of where I think this is a little bit cleaner. We can just do a policy ratio. Now it's not going to be one over the other exactly because it's the log value. So it's going to be torch dot what's it called? E to the whatever, exponentiated. So new log probabilities over the old log probabilities. The reason I'm subtracting these and exponentiating them is because this is essentially e to the new probabilities minus the old probabilities, which can be, right? So it's e to the new minus e to the old. And if we do a little bit of math, what we will see is that is the same as e to the new probabilities divided by e to the old probabilities. And because these are log probabilities, e to the log probabilities will get us the normal probabilities. So we end up with just the new over the old, I should say. It's a new log probabilities and the old log probabilities. So we end up getting the same thing, essentially, is what I'm trying to say here. It's just doing it a little different mathematically. But we get the same thing we were looking for. So we have our policy ratio. What is next? Well, the next thing we'll want to do is do this clipping thing. So we'll want to calculate this clipping thing. Essentially, we calculate so we'll calculate this inner part first, this clipping of the policy ratio. And then we take that and multiply it by advantages. We do the same thing for the non-clipped value, and then take the min of both of those. So let's go ahead and do that. So we have the policy ratio. Let's zoom down a little bit. Let's get the clipped ratio. It's going to equal policy ratio dot clamp. Clamp is clipping in Torch. That is the word for it. I don't know why, but yep. Let's do 1 minus self.ppo clip value. So this is, remember, this is 0.2 for us. So this will be 0.8 to 1 plus that value, which will be 1.2. So we'll be clipping the policy ratio to, in between 0.8 and 1.2. And then we will, from that, be able to calculate the loss, right? So let's see, how are we going to do this? So we have the clipped loss is the clipped ratio times the GAEs. And this is the right side of this right here, right? This is the clipped value times the GAEs, or the advantages. And then on the left side, we have the same thing without the clipped value. So it would be the full loss is going to be the policy ratio times the GAEs. And then to finish this off, we just do a min over both of them, right? So policy loss, the actual loss, is the torch.min of the full loss and the clipped loss. And we're going to min over these so we get a single value. Now, one thing you might maybe notice is, remember, this is our objective that we're trying to maximize, right? We're trying to maximize the advantages we get. But here, this is a loss, so we're going to want to make this negative so that we can actually minimize this instead, because in PyTorch, it's usually just easier to minimize things because they have a function for that. I don't know if they have a function for maximizing. But anyway, we got our loss, so we can go ahead and say policy loss dot backward, and then self dot policy optim dot step. And once we do that, we should be updating our policy. Awesome, 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 awesome. Now, one thing you might have noticed, and oops, I should have indented that. One thing you might have noticed here is, before I told you, proximal policy optimization, essentially the loss function is crafted in a way that we can use it multiple times. We can make multiple updates with the same batch of data. So we could just call this function multiple times, but that's a little bit messy, so I'm just going to include that in here. So let's put a for loop around this to do this update multiple times. So we'll be updating, remember we set the default to be 80 times on this one set batch of data. So we'll say for range of self.max policy train iters. We are going to go ahead and do all of this. And then the other thing I said, remember, was we're doing the version of this where we are essentially just going to check every step if we've gone over the KL divergence limit. And if we have, we're going to stop this loop prematurely, because we've already essentially changed the policy enough. If we do too much more, we might ruin the learning by making too many changes. So we can calculate the KL divergence. It's just an estimate of the KL divergence of the old log probs minus the new log probs, and take the mean of that. This is just an estimate, not perfect. It's a Monte Carlo estimate. So then we can say if KL divergence is greater than this value, or I'll say greater than or equal to this value we have already created, or this we've set, which I think was 0.01, then we're going to break out of this loop because we've already updated enough. So that should be it for the training the policy. Let's go ahead and make the training the value function right now too. So def train value. And let's see, so we're going to need observations and returns. So this is very simple. We're going to do essentially self.value optimizer. Oh my gosh, I was not looking when I typed that. So let me get this more in like the middle of the screen. But we're going to do a 0 grad when we start this. Then we're going to calculate the values, which is just going to be self.ac.value. This is the value approximation function. we're going to pass in our observations. So we have our value estimates for these observations. The loss is calculated super simply. It's just an L2 loss, so the returns minus the values squared. Simple L2 loss, nothing more to it. And then we are going to just go ahead and calculate the mean. And this should be value loss, my bad. Once we calculate the mean, we have our itemized loss. So we can just go ahead and say value loss dot backward and self dot value optim dot step. So very simple stuff, right? We calculate the values we get. We calculate the returns that are the quote unquote ground truth. This is Monte Carlo though, so it's an estimate. So this is the L2 loss, and we just backprop on that. Not too much more to it. This too though, remember we're also going to update this multiple times, so we are going to update it. Value train iters. Remember we set this before too, right here, so 80 times. You can change this if you want. But again, I already messed around with it and this worked out for me. Might depend on if you're using a different environment though, you'll probably want to change this. So there we go. There we go. We have the train value and train policy functions. We're going to go ahead and test those in a second. But I guess really before we test those, we need to format the actual data. We've stored the data, right? But we don't actually have a training loop where we call this yet. So that's what is going to be next. We need to work on the training loop. So let's go down to our training loop all the way down here. And what do we have to do here? We still have to, let's see, we have the train data, but we need to format it and then pass it into these training functions we just made, right? Yeah, so let's go ahead and do this data formatting. The first thing is the observations. We will make a torch tensor on train data. Remember this is essentially what we're returning right here, right? So observations are the first thing in this list. So we'll grab the 0th index. And we will then, let's see, what do we want to do? We want to set the data type to be torch.float32. What else do we want to do? We also want to set the device equals to the device. This is set to the CPU right now. We can change this later to a GPU if we would like to. Now, this is all good and dandy. I do also want to randomize the order of these just to be safe. It never hurts. So let's randomize it. We could just randomize these afterwards, but the problem is that we need to randomize them along with all the other data, right? Because after this, we'll have the actions and then we'll have the advantages and all that. Now, if we don't randomize them in the same order, they will essentially be matching up like the wrong action, like a time step of an action of time step 5 with an observation of time step 20, and that's no good. So here's a way to shuffle data together. A fancy little way to do it. We can calculate certain indices that are calculated randomly. So these are random indices from 0 to the length of the train data. And we can just index on these. So we can do permute indices. So if we have like, I don't know, 0, 1, 2, 3, 4, maybe this will end up being like 0, 1, 4, 2, 3 or something like that. It's just randomized. The thing is, if you index on 2 different arrays, they'll be randomized in the same order or shuffled in the same order, which is what we're looking for. That's good. Let's go ahead and move this to the next slide. Next thing we need is the actions. I'm going to go ahead and copy that over because it's the same thing as this, except for the data type is an int 32. The next thing we need are the GAEs. We haven't calculated the GAEs yet, right? So we're going to go ahead and do that in a second, but I'm going to skip it for now. We'll come back to it. But we also need the log probabilities, which is going to be pretty much the same thing as here. And that's all we need for the policy. Then for the value, so this is like, I guess, policy data. I should capitalize that or it's going to bug me. Shuffle. And then we also need the value data, right? The value data will essentially just be the returns and the rewards. So to do that, or I guess we don't even need the rewards, we just need the returns. Now we haven't calculated the GAEs or the returns yet, so let's go ahead and do those sort of in one fell swoop. Now if I'm going to go ahead and essentially copy over functions that calculate these. So here are the utility functions. I'll put them in here. Let's see, I have a few of these, or a few, no, I have two. So there's discount rewards and calculate GAEs. Discount rewards will, if you don't know what discounting rewards are, I recommend you check out my RL theory video. It will explain it, but essentially it means that we're prioritizing more immediate rewards slightly more than rewards that are further out. There's some other implications there, so if that's confusing to you, make sure to check out my RL theory series. Calculate GAEs, or general advantage estimates. This isn't something I've talked about on the channel. It's a paper, and I would go through it in this video, but it's actually quite complicated math-wise. The concept is fairly simple, but when you actually look through this, there's lots of math. So I'm going to leave it out of this video. You can either trust me that these are estimates of the advantages, or you can read through this yourself, or maybe if you're interested in a video on this, I can do that. Go ahead and post a comment if that is something you want to see, though. But for now, I'm just going to post these here again. This isn't what the video is about, so I don't want to get bogged down with just these details. But we have those functions now, so let's go ahead and use them. The discount rewards just takes in rewards and a gamma value. The calculate GEs takes in rewards and values, then a gamma and decay parameter, and then calculates the advantages, or the advantage estimates. So for the advantage estimates, I actually want to do that in the rollout. It just makes a little bit of sense. It just makes sense to me. So let's see. To do this in the rollout, so I have something I'm referencing. This should be fairly simple, and it should just be train data 3 equals calculate GAEs, and we just pass in the train data 2, which was, I'm forgetting, what was this? This was the 0, 1, 2, the rewards, and then I think the values we need next, which is train data 3. So we're essentially turning these values, instead of returning values, we are going to be returning advantage estimates. Yep. And last thing, so yeah, I guess we could replace this with GAEs if we wanted, but technically we're storing values and then converting them, so it'll be fine. Now, just in case, I forget if this is necessary or not, but I'm also going to convert all of these sort of arrays of data we're storing, or lists of data, into arrays. It should make them easier to index, just in case there's any problems. I'm probably doing this for a reason that I forgot, but yeah. Cool, so that's the new rollout function. I'm gonna go ahead and rerun this in case I've forgotten to run anything at this point. So just overview of what we've done so far. We created a model that outputs a policy and value model. Created the PPO trainer, which does the training for the policy and the value, as well as holds some parameters for the training. We have these utility functions that calculate the discount rewards and the general advantage estimates. We have a rollout function, which does exactly that. It does rollouts and returns training data and rewards. After that, we go ahead and what are we doing here? We have the environment, initiating that and initiating our model and running a quick test. Hopefully that works. Yep. And this is something we haven't done yet. We should probably do this real quick. Initiating the PPO trainer and parameters, because remember, we just created that. So we do need to instantiate that. This is super simple. I guess these are the values I ended up using. It looks like I ended up using 40 instead of 80 for the train iters. KLA version, so it looks like I'm using 0.02, and it looks like I also changed the value of the learning rate. So I don't know why I had those values up there. I must have forgotten to change them. But these are the values I guess we'll be using. And then we also, let's say, I guess we'll be doing 200 episodes in print frequency. We have that right here, though, so let's go ahead. We can delete this now. And run that. Hopefully, PPO trainer takes no arguments. Oh no, what happened? What did I do wrong up here? PPO trainer. Oh, looks like I forgot that. Let's try this again now. Awesome. So it looks like that's good. So back down here, we have essentially everything instantiated. We just need to do the training now and format this data. So now that we have those utility functions, sorry, that took a bit, but we can come back here and calculate the GAEs, or not calculate them, they're already calculated now. So we can put them in here. Remember, they're where the values were before in slot 3. So we have the GAEs. We have everything we need for the policy. Now we just need the data for the value training. So for that, for the value training, we need the returns. The returns are going to equal this just discount rewards function we made. And we just give it the rewards, and it will discount them for us. Super simple. And we'll permute these too. commute indices. And then let's make sure we go ahead and convert this to a tensor of floats. So we can pass it into, on the right device, so we can pass it into our policy training. So we've formatted all the data. We have everything we need. We have the training functions. Now we just need to pass it in. So this should be super simple if it doesn't break. Hopefully it doesn't break. So we're going to train the model here. So that should be PPO. Is that what I call this? Yep, PPO dot train policy. I believe it was train policy. Is it not called train policy? Train policy. It is. I don't know why it's not popping up. So train the policy, and we need to pass in the observations, the actions, the act log probabilities, the old ones specifically, and our GAEs. And then for the value training, we just need to do PPO.train value, pass in our observations, and pass in our returns. And sorry. So long as these functions work as expected, which I probably had some typos, so they probably won't. But if they do, this should work. This should increase the average reward. So you could see before, just random actions were getting us around a 20 average reward. Let's see if this works. Can't. Okay, it does not. I'm going to go ahead and figure out what's wrong here. Looks like GAEs can't convert indie array of type object. Interesting, interesting. Give me 1 second. I'll figure out what's wrong here and then be right back with you all. Okay, I'm back. I think I figured out what the problem is. Let's see if it is. I'll test it with you all so you can see how I'm debugging this. Essentially, I came down here and printed out the, what's it called? The GAEs. Looks like they are in a nested tensor. So these should just be single scalars. And I think the reason for that is because the value I'm calculating here and the action, I'm surprised it's actually working. I think these are both actually sort of nested tensors, because when I pass this into the model, this observation, I have to pass it in as a list of observations. So we're getting a list of values in Logits. So what I'm going to go ahead and try is, I think we should do this right here, and say the action and the value equals act.item and the value.item. And this will convert these tensors into normal Python scalars, if I'm correct. Or is it NumPy scalars? I forget. But hopefully it will work as NumPy scalars. I don't think that's even a thing. What am I saying? Just got to remove this because I'm already doing it down here. Oh gosh. There we go. Let's see if, okay, that looks a lot better. Let's go ahead and try running this whole thing now. Oh no. No train policy. Oh, didn't I check that before? Maybe I misspelt it. Train policy. Oh no, it's all indented one too many times. That's funny. Okay, now let's run all this. And oh, okay. It's taking 44 already. That's looking pretty good. 89. Wow. See, this is what is really great about proximal policy optimization. Already, we're training on a CPU, and just a couple seconds in, look at that. We have already hit about the max reward, because the max reward, remember, is 200 from this environment. So this is pretty good. This is what we were hoping for. I'm glad this worked so smoothly. You can see proximal policy optimization. There's kind of a lot here, but the actual training functions themselves are fairly small. The majority of the work is just in the data formatting, but proximal policy optimization is quite simple when compared to lots of other reinforcement learning methods, and it works super well. And that's one of the main things I think OpenAI was aiming for when they came out with this paper. I don't have the paper here, but one of the things they pointed out, right, is that this was a simplification of TRPO, which came before it, and it was supposed to be easy yet efficient. And here you can see that is exactly what it is, or at least relatively easy. So that's all I have here. Quickly going over everything we did, or I guess we kind of already did that. So the just last things we did to finish that up was we made sure the PPO trainer, I guess everything was good here. It was really just slightly modifying the rollout training data to be in the right format. And then once we get all this data, we pass into the training functions we made, and voila. I hope this was informational. I hope you learned something from this. And if you did find this helpful, leaving a like on the video, subscribing to the channel, it really helps out, and I really appreciate it. So if you do want to, go ahead and do it. I'm not forcing you, but anyway, that is it. That is all I have for this video. So thank you so much for watching, and I hope to catch you next time.